The Physics of Interstellar Travel. Chapter 10, Solar Sails. One of the counterintuitive things about special relativity is that although photons have no mass, they do have momentum. So if photons reflect off or are absorbed by an object, they will change its momentum and so accelerate it. This is the principle of a solar sail. In this chapter, we examine their basic mechanics and how we might use them for interstellar travel. The energy E and momentum P of photons are related by this expression, where c is the speed of light. If these photons are absorbed by a surface, then from Newton's second law, the force they exert on the surface equals the intensity of the light I, the power per unit area, times the area of the surface divided by the speed of light. As pressure is force per unit area, F over A, the pressure exerted by absorbed photons equals the intensity of the light divided by the speed of light. If instead the photons are perfectly reflected, then from conservation of momentum, the pressure is twice this, so 2I over c. We can use this to study the kinematics of an illuminated sail, which we consider to be a thin, flat, rigid surface. The acceleration caused by the radiation, the photons, equals the force, pressure times area, divided by mass, and we can write this acceleration in terms of the mass per unit area, denoted here with the symbol sigma. When the sun is the photon source, the intensity is related to the solar luminosity, the power, denoted here L subscript sun, and to the distance r of the sail from the sun via an inverse square law. When the sail is pointed directly at the sun, this force from the solar radiation pressure acts radially outwards on the sail. The other force acting on the sail is the gravity from the sun, which points inwards towards the sun, and so also follows an inverse square law. The ratio of the magnitude of these accelerations, denoted lambda, depends on the luminosity and mass of the sun, and on the mass per unit area of the sail. But the ratio is independent of the distance from the sun because gravity and radiation pressure act in opposite directions and both follow an inverse square law. When we plug in the values for the sun into this expression, we find that this acceleration ratio, lambda, is 1.53 times 10 to the minus 3 divided by sigma, in SI units, of course. This means that when the sail has a mass of about 1.5 grams per square meter, then the gravitational force and the radiation forces are equal. This is a very small mass per unit area. It's about 10 times less than typical plastic food wrap. So sails have to be extremely light for the acceleration from the radiation to be significant compared to the acceleration from gravity. This acceleration ratio is an important quantity in characterizing solar sails and is called the lightness number. We can now write Newton's second law for a sail moving in the gravitational field of the sun as this equation, where r is the 3D position vector of the sail relative to the sun. When lambda equals 0, there is no radiation pressure on the sail, and we recover the normal equation of motion that leads to the Keplerian orbits that we looked at in chapter 4, such as closed elliptical orbits or open hyperbolic orbits. When lambda equals 1, the gravity and radiation forces cancel, so the sailcraft does not accelerate. It either remains stationary or moves in a straight line, depending on the initial condition. For values of lambda between 0 and 1, the radiation pushing the sail acts to effectively reduce the gravity of the sun. Provided the sail is kept pointed at the sun, the net force is radial and varies with the inverse square distance, so orbits are still Keplerian. When the sail is so light that lambda is greater than 1, the net force is outwards. The spacecraft is not bound to the sun, and the orbits are hyperbolic, but now flipped. Exactly what orbit a spacecraft has depends not only on the value of lambda, but also on the initial position and velocity. One interesting case is when a spacecraft starts out on a circular orbit of radius r. The velocity of such a spacecraft is the square root of gm over r, and the escape velocity is root 2 times this. When the spacecraft now opens a sail and points it at the Sun, its velocity does not instantaneously change, but the radiation pressure lowers the net inward force, so the escape velocity is reduced by a factor of the square root of 1 minus lambda. Comparing these two numbers, we see that if lambda is greater than a half, the spacecraft's velocity will now be above the new escape velocity, and it will now be on a hyperbolic orbit and so unbound. This is a way for a spacecraft to escape from the solar system and go on an interstellar journey. When we analyse this problem in a bit more detail, we find that once the spacecraft is far enough away from the Sun for the radiation and gravity to be negligible, its velocity is given by this expression. The velocity increases only with the square root of the lightness number, but increases inversely with the initial orbital radius. So to maximise the velocity of the departing spacecraft, we should get the spacecraft as close to the Sun as possible before opening the sail. Suppose the spacecraft starts in the same orbit as the Earth about the Sun, indicated by the dotted line here marked 1. We could use a rocket to provide a large retrograde delta V to slow down the spacecraft so it drops close to the Sun. This manoeuvre puts the spacecraft on an elliptical orbit that takes it very close to the Sun, the solid line labelled 2. When the spacecraft gets to perihelion, its closest approach to the Sun at point P, the sail is opened, and if the lightness number is large enough, it flies out on a hyperbolic orbit. In this scenario, the velocity of the spacecraft at infinity is given by this expression, where Ra is the size of the initial circular orbit 1, and Rp is the perihelion distance of the elliptical orbit 2. If we could make a sail with a ridiculously high lightness number of 500, for example by making it out of graphene, and could bring it to within 5 solar radii of the Sun, which is twice as close as NASA's Parker Solar Probe has reached, then the above equation predicts we can achieve a velocity far from the Sun of about 1.5% the speed of light. This would cover the distance to Proxima Centauri in 210 years. Now, we're nowhere near anywhere being able to build the kind of sails required for this, but it is a viable alternative to fusion rockets, for example. Nothing like the Sundiver has yet been built, but more modest solar sails have been deployed in space. An example of this is the LightSail 2 mission of the Planetary Society from 2019. This CubeSat, with a mass of just 5 kilograms, was launched into low Earth orbit by a conventional rocket. The satellite then deployed a reflective sail 4.5 microns thick that had an area of 32 square meters. Its lightness number was around 0.01, far less than what we need for a Sundiver, but it demonstrated some important aspects of a solar sailcraft. Other sails have been tested too, and there are concept studies to build sails hundreds of meters in size, with lightness numbers close to 1 that could travel beyond the orbit of Neptune within a few years. There is a lot more to solar sails than I've covered in this brief introduction. In the book chapter, I also consider the case of imperfectly reflecting sails, how hot the sail will then get, what happens when we don't point the sail directly at the Sun, and how thin we can make the sail before it becomes transparent. In the next chapter, we'll take sails to a new level by turning up the radiation intensity by orders of magnitude, by replacing the Sun with lasers.